Okay, thank you very much to the organizers for the invitation. Yes, so the title of my talk is Feigin-Frenkel image of Witten-Kontsevich points. So very roughly speaking, the aim for my talk is to describe two different occurrences of Segal-Sugawara operators that in a certain sense are related by local Langlands duality. You can ask, well, how is it related to the main themes of this conference? So it turns out the basic setup of this duality involves meromorphic connections associated to affine Lie algebras, which are special cases of the connections we already saw earlier this morning involved in ODE-IM correspondence. Okay, so a little bit more precisely, let me fix a simple Lie algebra G. Let me denote associated untwisted affine Lie algebra as G1. For most of the talk, I will assume G is simply laced. The results carry over to the general case, but it's most nicely stated in this situation. Okay, so very loosely speaking, the scheme of the construction of ODE-IM corresponds by Masoero, Raimondo, and Valeri is of the following sense. You have some differential operator nabla. You look at certain solution psi, and you construct solution to Bethe-Ansatz equation as described in much more detail earlier today. So these nablas are vary to a certain family of meromorphic connections, maybe on P1 or on the disk, and associated to the affine Lie algebra G1. So let me fix some Lie theoretic data. Let EI and Fi be Chevalier generators as I goes between 1 and the rank of G. And let me fix a generator capital E0 of the lowest root space of G. So very concrete for SLN and standard M/N matrix realization of trace 0, you can take this EI to be EI I plus 1, Fi the transpose E0 to be En1. And some more notation for the affine Lie algebra. Right? So as we saw earlier, it's usually useful in this business to not work with the affine Lie algebra as abstract Lie algebra, but in terms of concrete loop realization. And so we want to fix a loop variable, which I will denote by Z, so that the affine algebra is some extension of this space of Laurent polynomials with coefficients in the simple Lie algebra G. An important object is what would be called the constant cyclic element, lambda Z, where you take the sum of the positive Chevalier generators of the simple Lie algebra plus Z times E0, where E0 was a choice of generator of lowest root space. So I believe I have different notational convention than in Raimondo's talk with respect to what is the loop variable. So for SL3, this is an example with standard choice. Okay. So now let me give some more details about the connections that I want to talk about. So they have two parameters, H and P. H is a parameter in the Cartan subalgebra associated to our choice of Chevalier generators. P is a potential function. And then with these choices, this differential operator is ddx plus hox plus sum of the EIs plus P times E0. And for the duality that I'm talking about, we specialize this a little bit, which is essentially what these authors call the G-Airy case. So H equal to 0, potential function just minus x, and we choose the evaluation representation of the affine Lie algebra at z equals to 1. Okay. So this is up to the sign. So instead of minus x, if you take plus x, I think this is what the G-Airy case notation comes from the relation for SL2 with the classical Airy equation. So then you obtain this differential operator, which I will call nabla ODE-IM because it will play important role throughout my talk, and I want to remind how it's a sort of a special important case of these connections out of which you construct solutions to Bethe-Ansatz equation. So some notation. So we had this constant cyclic element lambda Z. It would be convenient to slightly generalize this. So for any variable u, let me introduce some formal symbol lambda u where you replace the Z by u. So in terms of this notation, then ODE-IM connection is ddx plus lambda minus x. So let me circle back to what I said at the very beginning. It's the aim of my talk to describe two Langlands dual occurrence of Segal-Sugawara operators. Now I can say a little bit more. So they're related to this ODE-IM connection, and this whole story turns out to be related to quantum field theory, but probably in a little bit different way than maybe in previous talks. So the outline would be, I want to start by relating this ODE-IM connection to a special point in phase space of interesting integrable hierarchy, namely in the Drinfeld-Sokolov hierarchy associated to the same simple Lie algebra G, or untwisted affine Lie algebra. So to do that, first I need to give some description of this phase space, of which there are several. Right? Historically, in the early 80s, this was done in terms of what is now called affine opus. Back then, it didn't have such a fancy name. So, as mentioned in the Raimondo's talk, you have some underlying geometric structure on which you define this notion of opus. This can be done globally on a compact Riemann surface, or locally on a disk or punctured disk, which is the case of interest for the integrable systems. So I want to choose a coordinate on the disk. I would choose the coordinate x, where this is the same x as the ddx in these connections we mentioned earlier. So it's not the loop variable on the affine Lie algebra. So you could define the formal disk as the spec of power series with respect to x. I want to recall briefly two things. So the first is define the space of affine opus, which are the isomorphism class of that correspond to the phase space of the Drinfeld-Sokolov hierarchy, and then the closed variant of non-affine opus, which are essentially the Langlands parameters of local geometric Langlands correspondence. And this will be important later on. Right? Okay. So we have two coordinates. X is the coordinate on the disk of the geometric structure. Z is the loop coordinate of the affine algebra. And affine opus can be defined as ddx plus this constant element plus some formal power series with coefficients in the simple Lie algebra. But you have to have some conditions to have a good theory. So before I say what Q of x I want to allow, if you go to non-affine opus, you just put this spectral variable z to 0. And to describe which elements Q of x I want to allow and what are the gauge transformations, you should just think of triangular matrices for SLN generalized to general case, as was mentioned before. Slightly different description to Raimondo's talk is just you consider principal gradation. So you put the positive Chevrolet generators in degree 1, and the negative in degree -1, and then you can say the Q of x should be where the coefficients correspond to non-positively graded elements. So for standard choice of Chevrolet generators for SLN, right, diagonal or below. And then isomorphisms come from exponentiated adjoint action when now n correspond to sort of the things below the diagonal. So in terms of principal gradation, negatively graded elements. Okay. So just some examples. If you go to the ODE-IM connection, so you can think of this as a connection on the disk. Right, so what is Q of x? It's minus x times E0. E0 actually has degree 1 minus the Coxeter number, so in particular it's not positive. So that's an example of a non-affine opus. And similar, the collection ddx plus lambda z minus x is an affine opus, right? For the same reasons. And this affine opus we will encounter later on in the talk actually as, even though it's very simple, it has deep quantum field theoretic meaning. Okay, so of course there are many relations between integrable system and quantum field theory. Oftentimes the most direct transition is by a notion of tau function. And so this will be important for the duality I'm talking about as well. So in the context of Drinfeld-Sokolov hierarchy, there have been many works on constructing the tau functions. and most recently by Xiaozhong Wu, to give a good general uniform theory that now we know, take an affine opera, which from the point of view of integral system, the Lux operators of the hierarchy, how to say associate a tau function, which is in the framework we're working in, a formal power series in infinitely many variables. The variables are the time variables of the integrable hierarchy. So they're indexed by the set of positive exponents of the affine Lie algebra. Right? So as an example, for untwisted SL2, the positive exponents are the odd numbers. For G2 untwisted, plus or minus 1 mod 6 is the congruence condition. Right? And in general, you have a congruence condition where the modulus is the Coxeter number of the underlying simple Lie algebra. G. Okay. So it is known that you can define a tau function for each affine opera. And this will be the better description of the phase space to define the Witten-Kontsevich point that I want to do next, and then relate to this ODE IM correspondence. So the story of Witten's conjecture, Kontsevich's proof, of course, it has been told many times, so I want to be very brief, just recall those aspects relevant to the stuff I want to talk about. So in the early 90s, Witten conjectured that two different approaches to give mathematical meaning to the physical theory of two-dimensional quantum gravity give the same theory. So one is the topological gravity approach involving intersection theory of modular spaces of Riemann surfaces, and the second is the matrix model approach. And so the coincidence of those two theories has interesting mathematical consequences. In particular, matrix model approach directly linked to KdV phase space. So this topological gravity partition function should correspond to an interesting KdV tau function. And so how do you describe it? So one way is via the so-called string equation. And that will be the viewpoint we will take. So KdV hierarchy can be viewed as the untwisted SL2 Drinfeld-Sokolov hierarchy. And for each Drinfeld-Sokolov hierarchy, there is an analogous point that I want to now recall the definition. So if you want, you take this Lux operator or affine opera, you switch to the tau function viewpoint on describing this hierarchy, and then there's this differential equation. So H is the Coxeter number of G, and then this EG greater 0 is the positive exponents. Remember, they were the indices of the time variables of the hierarchy. And so you look at tau functions that satisfy this. Right? So in general, really, so beyond SL2, you really don't want to just think of tau as some form of power series, but remember, it is a tau function of this hierarchy. And so it's not obvious that there is such a tau that satisfies this, and it's not obvious that it is uniquely characterized by this differential equation. But okay, so in the generality that I need, this is the result by Cafasso and Wu, that there always is such a point in phase space, and it is unique. So proof is not that complicated. You can reformulate the string equation for tau function as a constraint on the dressing operator of the Lux operator, and then you just degree by degree with respect to principal gradation show you can solve this and solve it uniquely. Okay, and so the interesting so all of these points are related to quantum field theory in some sense, at least in the simply laced case in most direct way. I don't want to talk much more about that. Okay. So then you can ask the following. In these works by Cafasso and Wu, they use it to give very nice computations of the tau functions of this Witten-Kontsevich point, which corresponds to the partition function of the quantum field theory. But they also give a good algorithm for the dressing operator. But what about the affine opera itself? It turns out to be actually very simple. Okay, and so this was not given there, so for my purpose I needed it, so I proved this, that the affine opera of the Witten-Kontsevich point of the general G Drinfeld-Sokolov hierarchy, so this is not related, this doesn't need the simply laced assumption, is ddx plus lambda z minus x. So it's that affine opera I mentioned earlier. So very simple expression. So this also overlaps with results by Bertola, Duprov, and Young on topological ODE. Okay. Now, essentially by the construction, there's always a map from the affine opus to the non-affine opus that just sets the spectral variable z equals to 0. Right? So then if you observe this, then you see that the deaffinization of the Witten-Kontsevich affine opa is this ODE IM connection. Okay? So where are we? So I introduced this interesting connection, ODE-IM connection related to ODE-IM correspondence, and I show actually it's the underlying non-affine opa of the Witten-Kontsevich point, giving maybe an interesting relation to quantum field theory. Now, I want to come back to the main aim. Is okay, somehow there's two roles, Segal-Sugawara operators, whatever they are, I will introduce them. Two different roles they play, and there should be a Langlands duality. So the first thing I want to do is I want to revisit this Witten-Kontsevich opa from the point of view of Segal-Sugawara operators. So first step is to explain what are Segal-Sugawara operators are suitable generators in the center of a vertex algebra. Okay? So will be very brief. So you choose a complex scalar, the level corresponding to central action. Then for each such choice, it is known how to construct a certain vertex algebra V associated with the affine Lie algebra G1. Right? So what's the data of a vertex algebra? You start with the space of states, V. And okay, so what is it in our case? So it's related again to concrete realization of the affine Lie algebra in terms of loop realization, homogeneous realization. And this time I want to let x be the loop variable. Right? So there were this x and z. This time it's most convenient to let x be the loop variable, and then so the state space is sort of a piece of the enveloping algebra of the loop algebra, but you just look at the u minus of g, right? So you have this piece sitting inside of there corresponding to things with negative x degree. And then you have state field correspondence. You associate to each state a series in some indeterminate w with coefficients, endomorphisms of the state space, of course satisfying various axioms. But once you have that, you can define the notion of center. So the center z of g with our choice of lambda. Well, you look at those vectors in state space such that this field commutes with all other fields. Turns out to be a subspace of the state space and actually has the structure of commutative algebra. So now as we vary our level lambda, we get a family of commutative algebras that usually is just isomorphic to C. So the field of associated to a vacuum vector is just the identity. So you see you have at least this. But in this whole family, if you fine-tune your level to one specific value, this algebra gets much larger. So this so-called critical scalar choice, which is the negative dual Coxeter number. So again, this discussion doesn't assume that G is simply laced. So some Lie theoretic number, n for SLN, n plus 1 for SP2n. Okay, so let's look at this critical level center. So we take the vertex algebra with that nice choice of level, minus dual Coxeter numbers. Then it is known, follows some work of Feigin-Frenkel, we'll circle back to that later on, that this center as abstract algebra is isomorphic to polynomial algebra in countably infinitely many variables. But there's more structure there. This leads to the notion of Segal-Sugawara operators, or a complete set of Segal-Sugawara operators, which is sort of a finite set of generators. Now, finite, I mean, generating in what sense? This we should explain. So to do this, we need the third aspect of vertex algebra, which is a translation operator, right? A certain endomorphism of state space. So state space was u minus g, and then you can define an endomorphism of v, which is essentially negative derivative with respect to x, right? So that's how you define it on the piece of the loop algebra, and then you extend it to the enveloping algebra. It's known for any vertex algebra that translation operator maps the center into itself, and then the following question becomes meaningful. Can you find a finite set of elements in this critical level center that generates it in the sense that not only do you take these finitely many elements, but you're allowed to keep applying translation operator, right? Then you have a chance to get everything. Okay. It turns out the answer will be positive, so let us fix our notation. So let R denote the rank of the simple Lie algebra G. Then a complete set of Segal-Sugawara operators for G is a collection of elements Si, where I varies between 1 and the rank, such that they're all central elements in this critical level center, and that when you apply the translation operator, all of these elements are algebraically independent and generate the center. So that's how you get the infinitely many generators. And so a remark, these TJs, higher powers of translation operator applied to this, you could rephrase this in terms of the Fourier coefficients of the Segal-Sugawara operators, right? So if you apply the state field corresponds Y, you have some coefficients that are these SI sub Ks, and they're essentially up to some reindexing and scaling are these elements there. So the Fourier coefficients of the R, whereas the rank Segal-Sugawara operators are the generators or generate the critical level center. Okay, so you can ask, yeah, does it exist? So it follows from Feigin-Frenkel work that they always exist a complete set of Segal-Sugawara operators, and there's some way, if you think about them as elements of this U minus G, right? There's a notion of degree coming from loop degree, and this is known to be related to the set of exponents of the Lie algebra. And I don't want to get too much more detail, but I want to order my Segal-Sugawara operators such that the first corresponds to the first exponent, second to the second exponent, so on and so forth. Okay, so now what do we want to do with this? So because the elements in the enveloping algebra, they act on representations. Right? So they act on representations of G1. Which one do I want to consider for my considerations? The basic representation, which is a very interesting, well-studied highest weight representation of this affine Lie algebra. And now I want to assume G is simply laced. So Katz, Kashdan, Lipovsky, and Wilson have studied this basic representation a lot of details in the early 80s, not just in the simply laced case, but in this case, the theory is the nicest. So concretely, you choose a suitable Heisenberg subalgebra that's basically the centralizer of this constant cyclic element, and you choose a nice basis that corresponds to differentiation and multiplication, and then you do some vertex operator construction to extend this to the whole algebra. But note the following coincidence, or I don't know, but so this space of formal power series in these TIs was precisely the ambient space in which the tau function of the Drinfeld-Sokolov hierarchy is set inside. Right? So this is why we can achieve the current goal, which is describe this Witten-Kontsevich point, which was a special tau function, right? A special point in phase space, via Segal-Sugawara operators. So before say exactly how this goes, there's sort of one indexing subtlety. So the first Segal-Sugawara operator, which is related to the first exponent, which is 1, is always known to be a non-zero scalar multiple of the conformal vector in the vertex algebra. So what that means is the Fourier coefficients, so the coefficients in the field associated to it, they satisfy the standard commutation relation of the Virasoro algebra, but with a change in indexing by 1. Right? So in any vertex algebra with state field corresponding denoted by Y, if you look at the conformal vector V and then this associated field, VKW minus K minus 1, then LK, which is VK plus 1, they satisfy these standard relations. And so it will be convenient for what I want to do to reflect this shift in indexing for my purposes, because then the final result will be will be neater. So I look at these Segal-Sugawara Fourier coefficients Si sub k, and I do the superscript 1. So this is the first role they play. Later it will be a 2 to denote the action of them on the space of formal power series via the basic representation if I is not equal to 1. And then if I is equal to 1, I shift this index by 1 in the same way as we saw in the slide before. Okay. So then, if everything is suitably normalized, one can see that this differential equation on the tau function from the Witten-Kontsevich point, the string equation, can be reformulated as a very compact manner as this differential equation, minus derivative with respect to the first time variable plus the action of the minus first Fourier coefficient of the first Segal-Sugawara operator. And this gives us what we wanted to do, which was give a description of this Witten-Kontsevich point via Segal-Sugawara operators. So this, so far, was all the first role these operators play with respect to the Witten-Kontsevich point, and hence with respect to the ODEM connection, which was the underlying non-affine open. So what about the second one? All right, so the second thing is describe the second role, and this is a little bit different. So what I just did was, in some sense, pretty special for this special point in phase space. There's another way in which there's a construction over the whole phase space. And that's the second one. So describe all opers as functions on Segal-Sugawara operators using local geometric Langlands correspondence. Okay, so for the next couple of slides, we don't assume that G is simply laced. So Langlands duality actually is something interesting. So let LG be the Langlands dual Lie algebra, right? So we switch types B and C. Then what is the crucial deep result is the result of Feigin and Frenkel, which says, okay, look at this critical level center of vertex algebra of LG. Is isomorphic to the space of functions on the isomorphism classes of opers, not non-affine opers. And one could basically say this isomorphism is the local geometric Langlands correspondence. So, in terms of, if you think Fermat's theorem, elliptic curves versus modular forms, then these opers are the local geometric versions of the local Galois representations of the elliptic curve. And so this center corresponds to modular forms in the sense they will give rise to categorical representations. It would be analog of automorphic representation in the case of number theory. Right? That's how they construct Frenkel and Gates code, the candidate of local geometric Langlands duality. This is the right-hand side are the parameters, and the left-hand side corresponds to central action on the categorical representations. So when you combine this deep result with the de-affinization map that just takes the spectral parameter Z to 0, then what do we get? We get each element in this center, critical level center of LG, Langlands dual, yields a function by composition, right, on Drinfeld-Sokolov phase space. And particularly these Fourier coefficients of the Segal-Sugawara operators, which were the generators of this center, give functions. Okay, so before I relate those functions to what we did before, the first role of Segal-Sugawara operators, there's a different, much more elementary way to talk about functions on space of opers, which come from the fact that they have nice normal forms. And then, so when you have nice normal forms, you have a good chance to give very neat description of the dual space. So I want to give explicit description of the space of functions. Okay, so it turns out there's always you can choose a nice subspace V canonical of the simple Lie algebra G, such that every oper, we're talking non-affine opers right now, can be gauge transformed to a unique element of this form, DDX, plus some of the positive Chevalier generators plus V, where V is a power series with coefficients in V canonical, right? So in other words, the Q of X, which was the thing that changes, can be brought to a unique element in V. So then in other words, the space of isomorphism class of opus precisely corresponds to the space of power series with coefficients in V canonical. So you can describe the functions, right? You just read off coefficients. What does that mean concretely? So you choose a basis for V canonical, and then for each opa L, you let nu of L be the corresponding power series with coefficients in V canonical. And then you decompose this along the basis Vj, so each coefficient now is a power series. We choose the same indexing as one does in the state field correspondence. So the Vjk's are just some numbers now, so functions on these things are just reading of those numbers. Right? So define function Wjk that spits out Vjk. Okay. So recall Feigin-Frenkel isomorphism. You look at the critical level center corresponding to functional isomorphism classes of opus, and let Sj of Lg be the central element that maps under the Feigin-Frenkel isomorphism to Wj minus 1. A question, yeah?
Check means algebraic functions on.
Yeah, so it's it's this affine space V canonical X, so it's just the space of functions thereof, algebraic as a algebraic thing. And so Wj minus 1 corresponds to the constant term, right? Minus k minus 1 is the indexing. So this picks up the first thing, corresponding to the jth basis element, and then it is known that those Sj's, as j is between 1 and the rank, form a complete set of Segal-Sugawara operators. Okay, so...
Sorry, what is the question by tilde?
What is the what?
The question by tilde.
Isomorphism classes, right? So you have the opus, the way I defined it, a lot of gauge transformations, and so from this exponential adjoint action from the n, right, the lower triangle, and so.
I thought that question was the space.
No, I mean it depends how you set up notations. The way I set it up, I said opus is everything, and then you have gauge transformation. But yeah, I mean sometimes you say right opa. Okay, so. So then I denote by S I sub k with superscript 2 the functions on opus corresponding to this, these central elements via Feigin-Frenkel isomorphism. So now I've described two very different looking roads of Segal-Sugawara operators. I want to relate them on the case, or sort of, I want to show that there's an interesting relation pertaining to this ODE-IM connection or to the Witten-Kontsevich point in phase space. So remember the setup. So from now I want to assume that G is simply laced. So this has to do with the fact that if you look at this basic representation as the nicest description is simply laced case. So in particular, if you simply laced your self-dual under Langlands duality, so now there's no more LGs, everything just G. So what do we have? We have our space of affine opus. You could either go to underlying non-affine opus and then apply Feigin-Frenkel to get a bunch of functions from Segal-Sugawara operators. Or you could go a different route and you go from affine opus and you switch to tau function description and you apply Segal-Sugawara operators via basic representation. So you have two sets of operators. Now because we're simply laced, they're both associated to the same simple Lie algebra, but one of the two sides of this picture corresponded to the local geometric Langlands correspondence, right? So in this sense, they are Langlands dual, and there's sort of a hidden Langlands self-duality of the Lie algebra, and you could ask, is there some shadow of this? And I will show there's an interesting shadow of this for this ODE-IM connection. So to state the result.
Sorry, can you remind us what the map was from affine opus to CT? Right.
Yeah, just you take the tau function. So for each affine opa, there is an interesting procedure how to describe the tau function of this, right? So like think KdV has KdV tau function, right? Each Drinfeld-Sokolov. Okay, so to state this, we want to identify ddx with the derivative with respect to the first time variable, which is something that is the case for kp or KDV, or in general, Drinfeld-Sokolov hierarchies. And then in terms of this notation, the translation operator T is minus derivative with respect to T1. And now I want to choose two different, if you want, composition conventions. So if you take the Segal-Sugawara Fourier coefficients in their first form, I want to write S star T as additively S plus T. And for the second one, I want to write it multiplicatively. So composition with T. Okay. And then with this notational convention, I can state the main result. So the GB complex simply laced Lie algebra of rank R. Suppose you fix a complete set of Segal-Sugawara operators. It should be normalized in a suitable sense, because you make Lie theoretic choices on this stuff. For example, when you describe the V canonical on the set of opers, you make Lie theoretic choices. When you talk about Drinfeld-Sokolov hierarchy, right, the constant cyclic element, you have choices of what are your Chevalier generators, what is the generator of lowest root space, and so you kind of should align this stuff in a sort of suitable way. Okay, so then, if you have a tau function tau that's annihilated up to this T action via S1 minus 1, then you can ask, okay, what about the second? How do the second perspective act on it, which is the Feigin-Frenkel image of the title, right? Because if you have an oper, and of course you take affine oper, you pass the underlying non-affine oper, it corresponds to functions on Segal-Sugawara operators via Feigin-Frenkel map. So that's the Feigin-Frenkel image is some function on this. Okay? And so it turns out then for this tau function, from the second perspective, you always get 0 except when I is the rank and k is minus 1 again. So maybe better to say this result. The kernel of S1 minus 1 in the first way to think about Segal-Sugawara operators corresponds to the characteristic function of SR minus 1. So the hidden Langlands self-duality of this simply laced Lie algebra G is reflected in the interchange between first and last Segal-Sugawara operator, right? So the S1 is the first one, SR is the last one, corresponding to the first, to the lowest and the highest exponent, so 1 and Coxeter number minus 1. Right? And so this tau, just to remind, this tau function here is uniquely singled out by this because this was precisely the Witten-Kontsevich tau function. Okay, so to sum up, if you specialize the opers or the connections coming up in ODEM corresponds to the so-called G-Airy case essentially. They are related to the Witten-Kontsevich point and satisfy interesting Langlands duality with respect to the two dual actions of Segal-Sugawara operators. Okay, so thank you very much.
Any questions?
Yeah.
Very naive. So you consider an important special case of all persons related with do you expect or you think might be interesting to look at your result considering more general all persons or maybe
Yeah, so
it's an open
this dual viewpoint, of course, holds more generally. You can ask in general, yeah. So, for example, here I have this relation, it implies this relation. Yes, there's many other things we can ask if there's some interesting relations. I don't know. Probably something, but any other questions?
So, if I understand correctly, you constructed functions on the space of affine pairs by deaffinizing, taking z equals 0, and then applying the Feigin-Frenkel. But there are more general functions you can construct on affine pairs by going to this canonical form of affine type.
By going to canonical?
The integral summation of the KTV hierarchy are obtained by going to the affine canonical form, and then you integrate those over the circle, and you get more general functions on affine numbers. So
okay.
What would they correspond to?
I don't know.
I don't know.
In the tau
functions.
I don't know.
Okay. Okay.